So the next group that we were going to look at was solving problems where you have a log on each side. And there was a new piece of information in the directions that I felt like needed its own video. So this one was the first time when we were solving these log problems that it told us to watch out for extraneous solutions. Well, what does that even mean? Well, what that means is this. When we're working these problems, graphically what's going on, when we're trying to solve a problem algebraically, we're using our algebra rules to really find the x value where these two graphs intersect. That's exactly what we're doing. And notice that algebraically right here we use the rule that says that if you have a log on both sides and it has the same base, you just drop the log and work with the rest of the equation, and then it's just regular algebra. They came up with x equals 7, and if you were to graph this, the left equation on one line and the equation that the log that was on the right side of the equation on another line, and then find where those two logs intersect, then this x equals 7 explains the algebraic solution. But extraneous solutions happen when we take a problem like this and we find an algebra solution, but then when we go and look at that algebra solution, we do not see that happening on the graph. So drop the logs and set those two things equal to each other. Add x to both sides, you get 3x. Add 3 to both sides, you get -1. Divide both sides. And it says that the answer should be x equals -1/3. But these two graphs obviously do not ever intersect. And the reason that we got what's called an extraneous solution is because when we're solving these algebraically, we're kind of assuming that our domain is all real numbers, when it's obvious over here that with log functions, our domains are not all real numbers. So if you'll notice the x value, -1/3, which is somewhere right in here, okay, that x value is not in either one of these domains. The domain for this one looks like it's somewhere going to be somewhere around, I don't know, more than 1 but less than 2. Okay, that's where the asymptote is. That's where it looks like the asymptote is right there. And this one has an asymptote right there. It looks like at -4. So this one starts at, we'll just say 1.4, I don't know, and then it goes to infinity. This one starts at -infinity and stops when it gets to -4. So it never goes to this x value. So the reason that we have extraneous solutions is because when we're solving it algebraically, we're just blindly assuming that that we're dealing with all real numbers, that the domain is -infinity to +infinity. The reason that we have to check is because these log functions have restrictions on their domains. They do not, their domain is not -infinity to +infinity, so we have to check and make sure that the algebraic answer that we get is in the domain, and that's why we call it extraneous.